Okay. Oops. Let me do that. Okay. Can you see this? It's good. All right.
Yeah, we can see it.
Okay, so I'm gonna go ahead and start. So the title of this talk is the intersection form of spin-4 manifolds and pin-to-equivalent Mahova invariants. So this is joint work with Mike Hopkins, Jianfeng Lin, and Xiaolin Danny Shi. So you all know who Mike Hopkins is. So Jianfeng Lin is a third-year moral instructor at MIT, who is a geometry topologist. And Danny is a grad student of Mike Hopkins. He's a 6th year right now. So this is a talk about applications of equivalent stable homotopy theory to the topology of 4 manifolds. So central problem in 4 manifold is the following question: how do we classify closed, simply connected topological 4 manifolds? So okay, so say N is such a manifold. So there are 2 important invariants of N. So one is the intersection form. That's denoted by Qn. That's a symmetric unimodular bilinear form over the integers given by the cup product. Another important invariant is Kirby-Zimmermann invariant. So that's a cohomology class, the first cohomology class of this manifold with coefficient Z-2. So that's an element in Z-2. It's either 0 or 1. So celebrated theorem of Friedman says that suppose we take 2 such manifolds, and M is homeomorphic to N if and only if they have isomorphic intersection forms and also equivalent KS invariant. So in other words, if we want to tell if 2 simply connected topological 4 manifolds are homeomorphic to each other, we can just compute these 2 invariants. If they're the same, then they are homeomorphic. If they're not, then they're not homeomorphic. So, so this tells us that these invariants are like good enough. We can just tell them. So the other side of this question is, if we have a pair of these 2 kinds of invariants, can we realize them by a topological 4 manifold? So we divide them into 2 cases. So when the bilinear form Q is not even, then any pair Q with any number 1 or 0 can be realized as such a topological 4 manifold. And if the bilinear form Q is even, so it's an algebraic fact that the signature of this bilinear form can always be divisible by 8, then only these pairs can be realized. So this completely solves this question, whether how to classify all simply connected topological 4 manifolds. So in particular, if we start with the bilinear form, this is basically saying if this form is not even, there are exactly 2 topological manifolds it can realize. And if it is even, then with this actual condition, this KS invariant is determined by Q, then there is exactly 1 topological manifold that can be realized, that can realize Q. Okay. So that's the complete answer for the classification of simply connected topological 4 manifolds. So let's move into the smooth category. So how do we classify all closed simply connected smooth 4 manifold? So we already have the list in mind. That's the list of all the topological 4 manifolds. We can build up from there. So theorem by Whitehead, Moncrief, Hirsch, and Kirby-Zimmermann is that if this manifold is smooth, so the KS invariant has to be 0. So one of the invariant in the smooth category for topological 4 manifolds is already decided. Recall that earlier, for a fixed bilinear form, there are at most 2 topological manifolds. Then, if we're working in the smooth category, then at most 1 of them could have smooth structure. So Claus-Friedman theorem, this is saying that in the smooth category, 2 manifolds are homeomorphic. It can be completely decided by the isomorphic, can be decided by the intersection forms. So therefore, we can label topological 4 manifolds by their intersection forms if they're already smooth. So then there are 2 natural questions. So basically, given a topological 4 manifold, are there any smooth structure? And if there are, then how many are there? So this is usually rephrased as we can also like rephrase these questions in terms of the given a symmetric unimodular binary form, can we realize this form by a smooth manifold? So these two questions are usually referred as the geography problem, namely, given a Q, can we realize it as a smooth form manifold? And suppose it can, the second question is usually called the botany problem. How many different smooth structure this one has? How many non-diffeomorphic form manifolds can this Q be realized? So the reason for these two names in four-dimensional topology is the following. If you think four-dimensional topological manifold as a field, then whether it has a smooth structure or not can be think of whether you can grow trees on this field. And if you can grow trees, then the further question is, can you actually have a rainforest out there? So that's the geography problem and the botany problem. So for the purpose of this talk, I'm going to focus on the geography problem. So namely, given a topological form manifold, is there a smooth structure? So in other words, given a symmetric unimodular binary form, can it be realized as intersection form of the closed simply connected smooth form manifold? Okay, so algebraically, the classification of symmetric unimodular binary form is kind of complicated, especially when it's definite. So for the definite case, it could be like really complicated. However, there's a groundbreaking theorem by Donaldson, which proves that if Q is definite, although we still don't know a complete algebraic classification of definite unimodular symmetric binary forms. However, when it can be realized by a smooth form manifold, it has to be either I or minus I. So I is the identity matrix. So that's rule out the majority of the quadratic forms, the binary forms. So most of them, in the case of definite, they cannot have a smooth structure. So only these two can. So this completely answers the geography problem when Q is definite. So then let's move on to the indefinite forms. So that's divided by two cases, not even and even. So what even means here is that if you take a pair of identical non-zero vector, the output has to be even for every non-zero vector. Well, I guess including zero as well. And not even means not even. So there is another algebraic theorem classifies indefinite forms. So when Q is not even, then it is isomorphic to a diagonal form with indices 1 or minus 1. When it is even, it can be written as copies of E8, that's an 8 by 8 matrix, and Q copies of 0, 1, 1, 0. For some K in integers and Q in natural numbers. So let's first talk about the not even case, namely all the inputs are in the diagonal and either 1 or minus 1. Well, you can directly see that it can always be realized by connected sums of copies CP2 and CP2 bar. CP2 bar means you reverse the orientation. So that answers the not even case. So the only remaining case in the geography problem is the even case. So it's like all the regions on the planet are charted with either you can grow trees or not. The even part, some parts are deserts, some part you can grow trees, and the even part is a part which we don't know yet, but there are some progress. So recall that any even form can be written in this form. So there are two variables, K and Q. By Wu's formula, it turns out you can, if it's simply connected and the intersection form is of that form, you can always realize that Q has a trivial second Stephen-Whitney class. So this manifold in particular has to be spin. And Rochling's theorem tells us K has to equals to 2P. So K is an even number here. So by reversing the orientation, we may further assume K is bigger or equal to 0. So with that in mind, for the remaining cases, there is this 11-8 conjecture. So this conjecture is stated even in a more general case. We don't even need the simply connected condition in here. So the form.
Zhouli, can I interrupt for a second?
Yeah.
E8, the matrix E8. Is
yeah.
That something we're supposed to know, or is that just some specific thing?
It's a specific matrix, and if you search in Wikipedia, it's an 8x8 matrix. It showed up in a bunch of different things. It's an explicit matrix. It has input 0, 1, maybe -1, 2, and things like that.
Okay, thanks.
Yeah. Okay. So yeah, as I said, it's a purely algebraic classification that it can always be written as things like that. So then the conjecture is asking when this form can be realized, and conjecture that is if and only if Q is bigger or equals to 3p. So I will explain why it's called 11.8 conjecture. This is one of the version. So the if part is straightforward, namely, if P and Q satisfy that condition, it can always be realized for the following reason. So there is this complex surface. It's called the K3 surface. We know its intersection form is of this form. And we also know the intersection form of S2 cross S2. If you take the connected sum of these guys, we can realize everything when Q is bigger or equals 3p. So therefore, one side of this conjecture is trivially true. We can always realize that. So the major problem is if it can be realized, what can we say about the relation between P and Q? So to do some linear algebra, so basically for the two matrix we have in mind, we know its signature and its rank. So that corresponds to the two invariants, the second Beatty number and the signature of this manifold. So another way of phrasing this is that for any closed smooth spin-form manifold, it must satisfy the following 11/8 conjecture inequality, namely the second Beatty member has to be greater or equals to 11/8 times the absolute value of the signature. All right, so what are the known progress on this conjecture? So when P equals to 1, so recall that we're trying to realize P and Q, and PQ are the multiples of the two matrices, E8 and 0, 1, 1, 0. When P equals to 1, assuming this one has no two torsion, Donaldson used an anti-self-dual Yang-Mills equation to prove that this is true. And later on, Korhammer used pin-2 symmetries in supervision theory to remove that condition and still prove the 11.8 conjecture with case P equals 1. And a later breakthrough is by Fruta. He combined Korhammer's approach with finite dimensional approximation and gives a result. He attacked this conjecture using pin-2 equivalent stable Homology theory. So I assume most of you are here listening to this talk because you want to know what's the connection here. So how does equivalent stable Homology theory has anything to do with this? So that's the thing I'm gonna try to explain. But before I do that, let me mention Fruta's theorem. He actually proved a 10/8 theorem, which is already very close. So in the case when Q is even, let's make a definition. So Q is spin realizable if it can be realized by a smooth spin form manifold. So Fruta proved that the bilinear form can be realized, is spin realizable only if, so we have to have Q is bigger or equals to 2p plus 1. So recall that 11.8 conjecture is stating that it has to be bigger or equals to 3p. So rephrasing in the linear algebra, this is saying for the simply connected case, if it's not S4, then it has to satisfy the inequality. The second Beatty number has to be bigger or equal to 10/8 times the signature of the sign plus 2. So, okay. So he proved the theorem by studying a problem in pin-2 equivalent stable Homology theory. And for the work I'm going to talk about today, we give a complete answer to this problem in pin-2 equivalent stable Homology theory. And here's the consequence of our main theorem. So if this bilinear form is spin realizable, then that's the inequality it will satisfy. So in the Fruta case, all the these numbers are 1. So we have a bigger number. It's not 3p, that would prove the 11K conjecture, but that's the thing we have. And as a corollary for the simply connected case, so when the manifold is not S4, S2 cross S2 or K3, it will satisfy the 10/8 plus 4 inequality. But that's not the only point of this statement. So we will further show that this is a limit of the current known approaches to the 11-8 conjecture in the sense I will explain later on. I'm going to explain that in terms of the pin-to-equivalent Mohover invariant. Okay, I'm not saying 11-8 conjecture is not true. I'm just saying with current known approaches, this is the limit we can prove. Okay, so so this is part I'm least familiar with, but I'm going to try to explain how Fruta connect all the form manifold theory to equivalent stable homotopy theory. And it starts from analysis. So suppose M is such a smooth spin form manifold. So one way to study a manifold is to study functions over it, or even PDEs over it. So the Silberg-Wheaton equations is a set of first-order nonlinear elliptic PDEs of this form. So the input is some section of some bundle over this manifold M, so is the output. And if we do some completion, that gives us a map between Hilbert spaces, infinite dimensional Hilbert spaces. And but it's not a linear equation, so this map is not linear, but it's still a map between infinite dimensional Hilbert spaces. So this map satisfies three properties. It maps to 0 to 0. It's a pin-to-equivalent map. So pin2 is a one-dimensional compact Lie group whose underlying topological space is a disjoint union of two circles. And it can be viewed as this set sitting inside of the quaternions. So this map coming from PDE actually has the following property. So the point here is that the inverse image of 0 can be seen as the solution of this map. And this one has an even better property that if you have this small ball near 0, the inverse image is bounded. So in other words, the outside blue region will map to the blue region over there. So with that in mind, when we look at this solid ball inside, we can model out by the outside. Then that gives us a representation sphere, namely a sphere with a group action. And so this map induces a pin-to-equivalent map between spheres from SH1 to SH2. But here's one of the problems, which is that, as I mentioned, they are both infinite dimensional. So that's not very good for the purpose of homotopy theory. We really want to study maps between finite dimensional spheres. So that's where Fruta's finite dimensional approximation comes in. So this map can be written as two parts. One is the linear Fredholm operator, which means the kernel and co-kernel are finite dimensional. And this non-linear part, which has the property that maps boundary sets to compact sets. So when we look at the H2 and look at the finite dimensional subspace of H2, which are transfers to the image, and we consider its inverse image, we can do the following approximation. We keep the linear part, and we modify the nonlinear part by projecting to the V2 part. So therefore, we get a map between finite dimensional spaces. So this approximation between finite dimensional spaces satisfies three properties. It still maps 0 to 0. It's still a pin-to-equivalent map. So recall that earlier it maps the blue region to the blue region. So in particular, if you take a sphere, then it will still map to the blue region. And after this approximation, although the outside part doesn't have this property anymore, but this sphere still has this property that it still maps to this blue region. So having this in mind, we can do the same thing, similar thing as we did. We can model out by this boundary of the sphere, and here we still model by the outside. So we still get a map between spheres, which are in this case finite dimensional, and they're both representation spheres. It has a pin-to-action, and this map is a pin-to-equivalent map. Okay, so that's the picture we have. We have a pin-to-equivalent map between representation spheres, and that SW APR is approximation of the map coming from PDEs. So it turns out people show that both V1 and V2 are direct sums of two types of representations of pin2. So the first one is just quaternions. Pin2 sits inside of quaternions, so it acts where it's left multiplication. It's four-dimensional real representation. We also have the sign representation. It's pullback of the sign representation of the C2, the CQ group of order 2. And the pin2 fixed point on these two types of spheres are both the 0 point and the infinity. So it's the trivial sphere in dimension 0. And this maps to 0 to 0 and infinity to infinity. So therefore, we're actually looking at a commutative diagram here. So S0 sits as fixed point of both spheres, and we have a commutative diagram like that. So it turns out that by a computation of Atiyah-Singer theorem of this index of this Fredholm operator, you can see that if the intersection form is of this form, then we know the difference of this dimension with this action pin2. So this can be viewed as a virtual pin2 representation of this form. So therefore, the stable Hom-Tibbe class of this map, which is called the Bauer-Fruitman invariant of this manifold, it's called invariant because it doesn't depend on any choice we made earlier on. It's just a purely stable thing. It doesn't depend on choice of V1 and V2. It doesn't even depend on the metric of this manifold. It does depend on the smooth structure though. That gives us the following diagram. So because we know the difference of the dimension so stably, we can just put the H side on the left-hand side and the R side on the right-hand side. And S0 still sits inside as the fixed points, or the geometric fixed point in the stable world. And this map is a map between equivalent spheres. So this is where it comes in for the equivalent stable Hom-Tibbe theory. We have a commutative diagram in the stable Hom-Tibbe theory with a pin2 action here. So let's make a definition out of this. So a Fruitman-Hauer class of level PQ is a stable map of this form that fits in this diagram. So recall that, so this inclusion of the fixed point actually can be rewritten as a powers of this class. So any A class is Euler class that sits in one copy. We can take the smash product or composition of all of them and to realize this map. So this is exactly asking, the definition is saying that this map gamma sits in this diagram. You can even think this as a relation in the ROG graded pin2 equivalent stable Hom-Tibbe spheres. So a summary is that further prove that if a bilinear form is spin realizable, then through all this machinery, there must exist a level PQ Fruitman-Hauer class. Note that this is not an if and only if. When we have a manifold, we have the bilinear form, then we can produce a map in the equivalent Hom-Tibbe theory and the commutative diagram in the last page. So using pin2 equivalent K theory, Fruta proved that the level PQ Fruitman-Hauer class exists only if Q is bigger or equal to P plus 1. So that's the 10-8 theorem of Fruta we mentioned earlier. Okay, so a natural question here is, for this purely algebraic topology question, what is the necessary and sufficient condition for the existence of a level PQ Fruitman-Hauer class? So why might even dream? The answer is if and only if Q is bigger or equal to 3P. So if that's the case, this will directly implies eliminate conjecture. And if this is not true, knowing the complete answer to this question will still be good in the sense of that we know the limit of the current method. So it turns out John Jones found a counterexample when P equals to 5. And furthermore, he made a conjecture of when what is the if and only if condition for a level PQ Fruitman-Hauer class to exist. And this is the conjecture he make. So he's not saying that it's going to be 3P. It's still going to be 2P, but plus a constant, depending on P mod 4. That's the if and only if conjecture. This is just a conjecture about maps between Rickenton spheres. So for the necessary condition, there are many progress made by Stolz, Schmidt, and Minami. And before our current work, before the work I'm talking about today, the best result is given by Fruta and Kamitani. And their result is the necessary part, is the only if part, which is a number strictly smaller than Jun's conjecture. Well, for some part, 1, 2, 3, 3, and the conjecture is 2, 2, 3, 4. And so what about the sufficient condition? Well, it turns out not much is known for the sufficient condition. So for now, the best result is given by Birgit Schmidt in her thesis. She constructed a Fruitman-Hauer class of level 5, 12. And we completely answers this question, the if and only if condition. And that's our theorem. So a level PQ Fulton-Howard class exists if and only if there is this inequality. And know that the answer, depending on P, is a mod 8 periodic result. It's different from Jones's conjecture. So this is what Jones's conjecture is saying in terms of mod 8. And this is our theorem. And the right part is the difference. So 7 out of the 8 cases, the Jones conjecture is true, and 1 more case is not true. And that's the earlier Futa-Kamitani result. It gives one of the bounds. And the geometric corollary we have is a 10 over 8 plus 4 theorem that I mentioned earlier. It satisfies this inequality. And in the sense of classifying all Fulton-Howard classes, because we know exactly when a level PQ exists and when it does not exist, so this is really the limit towards the 11.8 conjecture for now. Okay, so aside from the whole geometric theory, as for a homotopy theory problem, this is really the chart we're looking at. We're asking when there exists a map between representation spheres such that this diagram commute. We want to classify all possible P and Q such that this diagram commute. So this is equivalent homotopy theory. So one of the great things about equivalent homotopy theory is this ROG grading. So just quickly recall that for any finite group of compact Lie group, and we have ROG is the real representation ring. So the point here is that classically we can map all n spheres to the 0 sphere. Equivalently, we can still do the same thing, but we have more spheres, namely the representation spheres. So therefore, we can map SV to S0, consider G equivalently. So therefore, this grading is much larger, namely the ROG grading. And we have this ROG graded stable homotopy spheres. So this ring is much more complicated than the classical case. So one of the phenomena we're seeing here is there are many non-nilpotent elements in here. So classically, we have the multiplication by P map. That's the non-nilpotent element. So equivalently, it still is. So the second family of examples is the following. We can take the G geometric fixed point from the pi 0 of the equivalent stem to the classical stem. And any pre-image, since the geometric fixed point functor preserves smash product, any pre-image of P is still non-nilpotent in the left-hand side. So that's another family of examples of non-nilpotent elements. Furthermore, if we take any V, which is a non-trivial irreducible representation, we have this inclusion of the 0 and infinity in here. So that's the stable Euler class. So it corresponds to an element in the degree -3. So this element, it turns out, is also non-nilpotent. All the parts of it is non-zero equivalently. You can detect it by equivalent homology, for example. So there are many non-nilpotent elements in the ROG graded stable homotopy spheres.
Hey, Zhouli, this is Dan again. I seem to recall there's some result of, I think, Erie that's, trying to do a Nishida nilpotent style results for geocovariant. And I think it's for maybe finite groups. Do you remember what that is or how these results fit in, or maybe the answers?
So my guess is, I don't know for sure, but my guess is maybe that's about the integer graded. But even in that case, there are still some non-nilpotent elements. I'm not sure what was the result we're talking about actually.
Okay.
Yeah. Okay, so let me move on. So there are many non-nilpotent elements in here. So why is this relevant to the story we were talking about earlier? So following Brunner and Greenis, we're making this following definition, the equivalent Mulhover invariant. So taking two elements in the ROG graded homotopy spheres. So the G equivalent Mulhover invariant of alpha with respect to beta is the following set of elements in the ROG grading. So basically, I'm asking how alpha is divisible by beta. If it's divisible by beta to the power of k, but not divisible by power of k plus 1, then the ratio is gamma, and there might be a set of that. It might not be unique. So we're calling this set as the equivalent Mulhover invariant. I'm going to explain later why we call this the equivalent Mulhover invariant. So we're mostly interested in the cases when alpha, beta, are non-nilpotent. So from this equation, one can compute the degree of it, the ROG degree of it very easily. So this condition is basically asks the following two diagrams. So alpha is divisible by beta to the k. So there exists a gamma that fits into this commutative diagram, but you cannot divide it even further. So there does not exist any gamma prime, which makes the right-hand side commutative diagram commute. Okay. So one can think this as relations in the equivalent homotypic booster series, but you can also think this as some kind of extension or lifting problem in the following sense. Let's start with alpha, and we can ask if it can be divisible by beta or not. But another way of thinking of this is when beta is one of the Euler classes, so this is really a representation sphere, then S0 sits as some skeleton, zero skeleton of SV. So this is more like asking, can we extend this map to SV? And when there are extensions, it may not be unique. So we should consider all the possible extensions. And we can, among all of this, we can ask if we can extend even further. And maybe some of them can, some of them cannot. And we can keep asking this question until all of them cannot extend. And this is the maximal extension we have. And therefore, knowing the degree of this maximal extension gives us back like how divisible alpha is with respect to beta. So in other words, knowing the degree of the Mahara invariant also tells us when this kind of diagram exists. So this is another point of view of thinking of this definition. So I'd like to talk about a few cases before we talk about pin 2. So C2 equivalently, so recall that ROC2 is generated by one sigma. One is the trivial representation, and sigma is the sign representation. So we have the classical Bousuk-Ulam theorem, that's unstable theorem between spheres with actions, with antipodal actions. If you take the unreduced suspension, it corresponds to the several copies of sign representation actually. So it actually follows from the following stable statement. So if we're thinking of A sigma, to the power of Q, and the Mahara invariant with respect to A sigma, the degree of it is 0. So namely, in other words, we have the following two diagrams. That's the definition of the Mahara invariant. The left-hand side diagram, of course, exists because we can just choose gamma to be the identity map, which has degree 0. But the statement is more like the right-hand side diagram does not exist. We cannot divide A sigma to the power of K by A sigma to the power of K plus 1. So this view implies that unstable map does not exist, and therefore the classical Bousuk-Ulam theorem. So it turns out these two theorems can be proved they're equivalent. So that's one of the cases, like A sigma, the Mahara invariant with respect to itself. And the connection to the classical Mahara invariant is the following by Brunner and Greenes. So consider the C2 fixed point. So take any non-equivalent map from Sn to S0. Consider the pre-images, all the lifts in the sense of the geometric fixed point. So this is a C2 equivalent map, although the action on the two sides are still trivial. So among all the lifts in here, try to do the maximal extension among all these elements with respect to the sigma component. Then we get a map, and we forget this map, forget the action. Then we get a non-equivalent map. So this is a non-equivalent element in the stable homotypic spheres. So the input is some element in stem n, and output is in stem n plus k. And it turns out this element gives you a non-trivial element. So Brunner and Greenes prove that this process in the equivalent world, through the equivalent world, is equivalent to the definition of the classical Mahara invariant defined using a Lin theorem, and so forth. So in particular, we understand the classical Mahara invariant of powers 2 very well. It turns out it contains the first non-zero element in the atom distribution Q in positive degree. So this is earlier study by Landweber in the sense of the C2 equivalent definition. And as we all know, this study by Mahoward and Ravenel, and later Brunner and Greenes shows that the two definitions are actually equivalent. So moreover, if you're just looking at the degree, which tells us how divisible it is, then we have a 4-periodic result in the terms of the C2 equivalent commutative variable. So for the C2 case, recall that our C2 is generated by 1, sigma and lambda. 1 is a trivial one. Sigma is a sun representation on the C2 then pullback. And the lambda is a two-dimensional real representation correspond to rotation by 90 degrees. So Michael Crabb, Birgit Schmidt, and Stefan Stolz, they studied the C4 equivalent Hopper invariant of power of A sigma with respect to A2 lambda. So Crabb actually also studied the powers of A sigma with respect to A lambda itself. And here's the result they have. So that's the degree that tells us exactly how divisible things are, and they have an 8 periodic result. Since C4 is a subgroup of pin2, then Minami and Schmidt used this theorem to deduce the non-existence of certain Furtama-Hopper classes and has applications in the four-dimensional topology. So in our case, so we're interested in P2, and that's the two irreducible representations we mentioned earlier. So by definition, a level PQ Furtama-Hopper class exists even and only if we have some inequality on the H part of the degree of this P2 equivalent Hopper invariant. To prove our theorem, we analyze the P2 equivalent Hopper invariance of power of AR with respect to AH. And our result in terms of Q, earlier we were talking about in terms of P mod 8, but in terms of Q mod 16, and this is also how we prove the theorem, it turns out it's the 16 periodic result. So if you look at the pattern in here, these three numbers are the same, so 3, 2 are the same, 3 are the same. And if this number 4, which is red now, is 3 instead, and those two columns will have a similar pattern, and our result will be 8 periodic, and Jones' conjecture would be true. So it turns out this corresponds to some very long sphere-based Thiel-Herzberg differential in a spectral sequence that correspond to some time spectrum over the classic Feldman space of P2. Maybe I will explain that later. So this is really the picture that implies our theorem. So I'll explain what this picture is, but let me just say that, so this line in here, we call this the Mahorber line. So this line actually implies the statement I just showed you. This implies our theorem. So this is some sort of cell diagram kind of thing. So to motivate this picture, I first like to talk about the classical Mahorber invariant in the C2 case with a little bit more details. So there's a map, which is a reflection. We have the sun representation sphere. The 2 points here are the fixed points, and the action C2 is the reflection. And this reflection also gives us a map between the two representation spheres. It's a C2 equivalent map. It turns out this element is not trivial, and it generates the pi zero, also known as the Burnside ring. So if you take the fixed point, it has degree 1. The underlying map has degree -1. So in particular, 1 plus this element chi has a fixed point which has degree 2. So therefore, this element, since fixed point, geometric fixed point preserves smash product, this element in this ring is actually a non-important element. So one of the questions we could ask is, what is the non-equivalent, what is the equivalent Mahorber invariant of powers of its element with respect to A sigma? So what Brunner and Green shows is that this is equivalent to the classical Mahorber invariant problem. The degree is exactly that degree of powers 2. So this is the right element when we lift with respect to the geometric fixed point. And this is the corresponding picture for it. So each column here is the shift of due of RP infinity minus infinity. And each dot here is, you can think that as a cell. So by Lin's theorem, each column here actually are homotypically equivalent to the sphere, but this can be seen as a more complicated cell structure. I'm drawing some of the the attached maps by 2 and eta, but not all of them. So there are, like, all these columns are the same, and there are maps between them. They map to the right, and that's a multiplication by 2 map. And there's also one more map to the sphere. It turns out this cell, these columns are not attached to all of them above it. So that's really like a top cell. So this is really like some kind of pinch map. So we have a bunch of maps. And the question here is, so by cellular approximation theorem, all the thing under this line, when you go map all the way to the sphere, you have to map trivially up to homotopy. That's just the cellular approximation theorem. So one reasonable question we can ask is, for what skeleton when you map all the way to the sphere, it maps trivially. And therefore we can make a definition. For example, if we take this column, and so all the gray part, if it maps trivially, we just like mark it as gray. And so this line means under this line, everything maps trivially. When taking all the compositions to the sphere, it maps trivially. And if we include one more cell above this line, then this skeleton maps non-trivially to the sphere. So therefore, we have a map for each column above this Mahorber line that maps to the sphere. And if we restrict to the bottom cell of this column, this map itself will have to be a non-trivial map. So that will correspond to an element in the classical non-equivalent homotopy spheres. So this problem is studied very well by many people I mentioned earlier. So in particular, we know exactly what's the Mahorber invariant of Popper's 2. Namely, we know exactly what the first cell above the Mahorber line that maps to the sphere. So there are some patterns you can see in this picture. So first of all, you see a 4 periodic pattern. So because they're maps by 2 and cellular approximation theorem, you know this Mahorber line is like a rising water level if you go to the left. And you can also think this is like climbing up the stairs. So you climb by 1, by 1, by 4, by 2, 1, 1, 4, 2, and so forth. So there is a 4 periodic pattern. And there's also all these elements. They're detected by the K1 local sphere or the J spectrum. So you can also see some periodic pattern of these numbers. Okay, so this is equivalent of computing the classical and the equivalent Mahorber invariants in the forms I mentioned earlier. So how do people prove this theorem? So one of the proof is the following. So we want to prove exactly where this line is. So namely, we want to give an upper bound of this line and a lower bound of this line, and we want to prove they're the same. So for the lower bound, one of the proof is we can use the result of TODA. So namely, if we cut 8 cells in each column, namely 4 copies of Moore space, when you go 4 columns to the right, the composition gives multiplication by 16 of the identity map. TODA proves that this map is always 0. So this gives us a way to inductively or directly prove the lower bound. So namely, suppose we already know the line in here. When we move 4 columns to the left, so naively, by the cellular approximation theorem, all the way from here maps to this column. But then TODA tells us, oh, if you just restrict to the 8 cells in here, when you go 4 columns to the right, it will be 0. So therefore, you can mod out these 8 cells further. So knowing you can climb up the stairs in here, that means when you go 4 decks later, you can climb up at least 8 more levels. So this gives us the inductive way of proving the lower bound. You can do that for any like 4 columns in between and things like that. So this proves the lower bound. For the upper bound, it's more like a detection theorem because we want to show if we include 1 more cell, it maps all the way to the sphere, it's not 0. So therefore, you cannot like quotient more cells out, you cannot go even higher. So this is proved by detection by KO theory. So it turns out every 2 out of 4, like eta8 square, pH1 square, they're detected by KO. So in particular, we know this map is non-zero. And for the other 2 columns out of 4, if we include 1 more cell, that's amount to Moore space, we know this skeleton maps to sphere non-trivially. That map is detected by KO. But if you check the dimension, they correspond to things like 8K plus 4 or 8K plus 8. So none of these elements in KO are detected none of these elements in the sphere are detected by KO. Because for KO, those 2 groups are Z. So therefore, you know the detection is here, but in the sphere, it cannot be that. So it can go down 1 lower. So therefore, combining this discussion, you know exactly the upper bound will also have to be this line. So it turns out the proof is that the lower bound, upper bound are two different approaches, and the answer turns out to be the same, and they're not dependent on each other. So that's basic summary of the classical computation. So in our case, it's much more complicated. It turns out for the lower bound, we don't have a local argument like that. We don't have like locally, if you just go several steps, it's 0. It is never true. And for the upper bound, we have to use some variations of KO. We have to use the J spectrum, KO, Q mod Z, and things like that. And moreover, our proof of the upper bound depends on the lower bound. So the two bounds are actually proved using each, the upper bound is using the lower bound. So I'm gonna try to explain what that is. So as in this case, we first translate this P2 equivalent problem into a non-equivalent problem, and this is a sketch. So C2 acts on the sphere, so therefore acts on the classified space, namely CP infinity, by the following action. So therefore P2 can be seen, the classified space of P2 can be seen as BS1 mod out by this C2 action. And let lambda be the land bundle associated to this principal bundle. So we substitute this fiber C2 into the real line, and we can consider all kinds of time spectrum over BP2, namely several copies of the virtual representation minus lambda. There are inclusion of sub-bundles of m copies to n plus 1, so the virtual bundle direction will be reversed. So that gives us a map between time spectrum. They're all over BP2, and just like that. So it turns out if we compute the co-fiber in the stable category, it corresponds to the desuspension of the suspension spectrum of CP infinity. And moreover, from geometry, BP2 sits inside of this fiber bundle. The fiber is a RP2 bundle over HP infinity on the space level. And therefore, this gives a cell structure for BP2 and also the time spectrum over it. So that's what this picture is about. So if you look at the last column, that's S0. If you look at the zeroth column, that's BP2. So BP2 is RP2 bundle over HP infinity. So that's a cell structure for RP2. And HP infinity has a cell in every 4 dimensions. It turns out the corresponding Larry-Serre spiral sequence just collapse. And that's the sum of the cell structure. We can even, by playing around with other columns of other time spectrum, and prove this either square attaching maps. For this column, the first column, that's the minus lambda time spectrum over BP2. So by the time isomorphism, we know it's homology, so that's the structure. And by some kind of James periodicity on the fiber, we can also describe its stimuli operations. It's still like every 3 cells in every 4 dimensions, and we have a gap here, and so forth. So that's what this picture is, and there are a bunch of maps. As I explained, there are maps between these time spectrum. So what is this? So a natural question we can ask is, what skeleton of this time spectrum maps to 0 if you map all the way to the sphere? And it turns out this problem is equivalent to the problem of computing the level PQ full-time Howard class in this P2 equivalent case. I'm going to sketch why that's the case. So recall that we want to know when such a diagram exists, namely when this map exists for P and Q. While we're in the stable world, we can just take the dissuspension of the co-fiber or the fiber, which is the unit sphere of this copy with a plus point. This map exists if and only if this composite is 0, therefore G is 0. So this map is powers of elements, the homotypic of the spheres. So the smash and composition, we can just play with it. It turns out we can rewrite this map, and we can smash over all these copies, and to realize this composite is the same as the following map. So G being 0 is the same thing as this map being 0. So note that away from the base point, this thing is P into X freely, and for the sphere, P into X trivially, so we can mod out by the P into action. So therefore, this composite is 0 if and only if analytically the following composite is 0. We're taking the homotypic orbit of mod out by the P into action. So therefore, we want to know when this thing, my sphere, is 0. That's the equivalent of knowing when this diagram exists. So let's focus on this gadgeting here. So P2, as I said, is a disjoint union of 2 circles. It actually sits inside this short exact sequence. So when mod out by pin2, we can mod out first by S1, then mod out by C2. So this R tilde comes from the sign representation. After we mod out by S1, that's just the sign representation for the C2 case. And this, after we mod out by S1, that corresponds to some skeleton of CP infinity. Then this residue C2 action on the CP level, by our definition of the time spectrum, that corresponds to exactly the skeleton of the time spectrum over between two of the virtual bundle of Q copies of the virtual bundle we defined earlier. So in summary, this diagram exists if and only if this map is 0, if and only if some skeleton of the Q's column mapped to sphere is 0. And that corresponds to this picture. So that's all the columns of the time spectrum, and we wonder like which skeleton of each column mapped to sphere is 0. And our theorem is that this is exactly the Mahorber line. It is the lower bound and it is upper bound, they coincide, and that's the line. And knowing this picture, we can reproduce the commutative diagram we talked about earlier. So for example, if you take this column, say this is the sphere, that's the 0th column. If we count, this is the 8th column. And knowing this line is saying that, recall that under this line, everything maps trivially to the sphere, but with one more cell above this line, everything maps non-trivially to the sphere. So recall that in here, each copy corresponds to a fiber in RP2, and that corresponds to a copy in SH, a copy of the quaternions, as in representations. So this is saying that we have 2 copies of H, and this is 3 copies of H. So this corresponds to, we're in the 8th column, so that's the 8th virtual bundle, that's the twist. So there exists a map from 2 copies of H to 8 copies of R tilde. So that's the blue part. And this also implies there does not exist map, because this map is non-zero. There does not exist a map from 3H to 8 copies of R tilde. So knowing this picture tells us exactly when certain PQ maps exist and when certain PQ map does not exist. It's a homotopy theoretical answer to that. It does not construct the map for the existing ones, but it does tell you it does exist, and it also tells you when it does not exist. So for the remaining time, I'm gonna say something about the lower bound part of this proof. So one key ingredient is the low-dimensional non-arithmetic stable homotopy of spheres, and that's the classical Adams power sequence picture for it. So I will not explain to you what that means. So, but the point here is you can read off relations from this picture. For example, this is like really low stem relations. In particular, many of the stems are 0, or some relations are 0. So the idea is that our result is a 16 periodic result. So that makes us want to still do this inductive approach. So suppose we're already in here. We already have the Mahorber line in here. And that means we have a map. So lower things map to sphere trivially, upper things map to sphere, and there's a map. So what's the problem here is that you see that because of the cellular approximation theorem, there's no cell in these spots. So therefore, when you move to the left, this Mahorber line, this border level will rise gradually like that. But that's not enough, because we want to prove, the problem is there is a big jump of the Mahorber line, of the border level. So therefore, we want to prove the dashed line here, 8 steps later. So we're first building up a lower bound for an 8 periodic version, then a 16 periodic later on. So the problem are these 4 cells. So compared to the classical case, they use Toda's result that if you have 8 cells, we'll go several steps later, it will go under the Mahorber line. It's a local argument. But in here, we know the case is that this is not true. So intuitively, 3 of the 4 cells will die after we go 8 steps later, but this cell and this cell is connected by 8 squared. So we know for sure, locally, this map is not. But it's still okay because the Mahorber line is defined when we map this cell all the way to the sphere. So we need to show this cell, when we map all the way to the sphere, it's 0. So how do we show this? Well, one of the things is maybe we want to build in more inductive relation when we do the inductive approach. So one thing to do that is we want to have some estimate, some control of this cell when it maps to sphere. If when this cell maps theory, if it's an element that's annihilated by eta squared, then we're good. So this is one of the points which our proof is more complicated than the classical case. Classically, we have very good control of what the bottom cell maps sphere is. That's somehow invariant. But in our case, we have to control two of the cells. So this cell is not attached to these two cells, by the way. Okay, so how do we do that? So we consider these 7 cells, because that maps naturally to the whole column in here. But study a map from a 7-cell complex to a whole column is very complicated. I'm running out of time, so I'm gonna say the ideas really quickly. So we want to consider the maximal the minimal subcomplex that contains this top cell. It turns out this cell is not attached to these 3 cells, it's only attached to these 3 cells. So this part we talk about, the dimension between these 2 cells is 6, so that use pi 5 is 0 because the attachment map is in 5. It turns out we can prove that these 4 cells has to map through the 3-cell skeleton, and moreover, we can gradually use this information and prove that these 3 cells map trivially in here. Now this is good for the inductive approach because we can use low-dimensional computation to show this composite has to be 0. The difference of dimension between this cell and this top cell is 8. And we compose it with eta squared is 0. And the difference between this cell and this cell is 12 and 13. So therefore, we know the composition of the 2 right arrows is 0. So therefore, we can get rid of this cell by doing this more complicated inductive approach. So for the induction, for actual induction, instead of saying anything, I'm going to show you a little movie. So this is the initial point of the inductive hypothesis. So basically, that's a rough intuition of how we think of this inductive approach. But the actual proof for this part is very lengthy. It's like 30 pages or so. And in particular, there's a very technical step, which is that we want to prove when the 4-cell complex maps the whole column, it actually factors through the top cell and maps through the 3-cell skeleton. And we have another mini movie for you. And the proof is by studying carefully of all the intermediate columns and the cell structures in between. But again, this is just an intuition of how we think about it. Proof. For the rigorous proof, is this part is also like 7 pages or so. So that's the last picture of this movie, and I will stop here. Thank you.
Okay. All right. We're just about out of time, but maybe we have a chance for a couple quick questions. Well, I had one question. You said that your, 10^8 plus 4 is sort of the limit of the method. And just to be clear about when you say the method, you mean using this, like the Cyber-Witten map and like looking for these Furuta classes, right? It's that method.
It's this method, exactly, yes.
There might be some entirely different way.
Yes, yes. It goes all the way from analysis, as you can see, all the steps, and I'm just talking about this. Yeah.
Right. Okay.
I have a question too.
Yeah.
So if the question got modified to classifying simply connected algebraic 4 manifolds, does that help? For instance, they're cool pin structures on many of them. There are cool quadratic forms associated with that algebraic structure.
So sorry, could you repeat your question? I didn't catch the starting point.
So assume not only smooth, but algebraic.
Algebraic, I see.
Any help?
I may be wrong, but I think the 11A conjecture is true for algebraic for manifolds.
Thanks.
Any other questions? All right, I'm going to unmute everyone again so we can thank him one more time. All right, thanks again. And we will meet again in 2 weeks. Thanks, everyone.